All right. Okay. So I'm happy to introduce our speaker today, Zhiyu Wang, who went to Carnegie Mellon as a undergrad student and then went to University of South Carolina as a PhD student and just joined us as a postdoc, as a Hale postdoc. Zhiyu works in graph theory combinatorics and has written numerous papers already. Uh, Today he'll talk about saturation problems in Ramsey theory, posets, and geometry. Okay, go ahead.
Thank you. I think the introduction is too formal for me. Yeah, so today I'll just talk about some saturation problems, but it's kind of different from the saturation problems that we heard before. It's more Ramsey flavored instead of extremal flavored. So this is joint work with Gábor Damásdi, Balázs, David, Casey, and Oscar. Much of the work was done during a trip to Budapest. Okay, let me briefly kind of talk about the relationship to extremal graph theory. So a very quick background: we know that given a graph, the theorem number, which is the theorem number of f, is the maximum number of edges in a F-free graph, which means that the G doesn't contain f as a subgraph. So following Mantel's work on triangle-free theorem in 1947, determined that the theorem number of Kr, the complete graph on R vertex, and that is so the extremal graph is the famous theorem graph where we have an R-1 partite graph, and then the vertex are evenly distributed, and then there's a complete R-1 partite graph. So how is it related to saturated? Given this F, we can define a G to be F saturated if G is F free. And then we also have this condition that adding any edge not in G will create a copy of F. So that is kind of the idea of saturated. Adding any non-edge will give us this, will break the property that we want to preserve. So in that sense, what is theorem number then? Theorem number of F is basically, if we take a F saturated graph, and then what is the size of the maximal F saturated graph, right? And then, so the natural analog would be, what about a minimal F saturated graph? What is the minimum size of a F saturated graph? And that is exactly the definition of saturation number. So we use SAT to denote the saturation number of F. There's another very natural definition of saturation. Well, the saturation concept really is represented by the second condition, where adding any non-edge gives us a F. So if we remove if we weaken the condition that G is F-free, then we call this the semi-saturated number. I think this is it appeared in many work before in different names. So this semi-saturated number is just the minimum size of a graph where we don't care whether it's F-free or not, but adding any edge will give us a new copy of F. So the only two differences whether G is F-free between the two versions. If there's any question, please let me know. Okay. So let's kind of briefly. So there's a lot of literature on saturation of graphs. So we'll just briefly go over some of them. So in contrast to the theorem number of Kr, Erdős, Hatchno, and Moen show that the saturation number of a complete graph on n-vertex is actually linear. So this is fixed R, then this is n minus R plus 2 times R minus 2 plus R minus 2 plus 2. Okay, so where does this number coming from? So in order to prove upper bound for saturation number, all we need to do is to give a construction. a construction of a graph that is F-saturated. And because then the saturation number is the minimum F-saturated graph, and then that construction will give an upper bound for the saturation number. So this is very easy to see where this number coming from. It's basically we have a R minus 2 vertex. Then the rest of vertex is n minus R minus 2. And then what we can do is we can have a complete graph within the R minus 2, and then a complete bipartite graph between R minus 2 and then the rest of the vertices. So that number adding up is exactly this, and it's easy to check that this is F-saturated. Means that if I add any non-edge, if suppose I put an edge in here, that will immediately produce a new copy of KR. Will give a copy of KR. So you can see that because there are R minus 2, and then if I have an edge here, I will have a KR. So another classical theorem is by Kazon and Tusa in 1986. They basically show that the saturation number of all fixed graph is linear. So it's all big O of n. And then in the same paper, Erdős-Szekeres and Moon just want to relate the saturation number and semi-saturation number. For cliques, KR, these two are equal. Okay, both, I think the example is both this graph. Okay, so apart from graph, we can talk about saturation, those kind of extremal flavors of saturation in many other settings. Okay, so as long as we have a structure, a discrete structure, and we have some property, we have some restriction, we can always ask about what is the extremal number, and then what is the saturation number. So extremal is the maximal, while saturation is the minimal. So for KR free, we know that the extremal is the theorem graph, the size of the theorem graph, and then the saturation is linear. If we look at R uniform hypergraph, and then the property we want to preserve is that all hyperedges are pairwise intersecting. Then the extremal graph, the extremal structure, this is exactly the Erdős-Szekeres theorem. Basically, the is n minus 1 choose R minus 1, and then the structure is that you take you put a single vertex which is shared by all the other edges. So there are n minus 1 choose R minus 1 of them. In contrast, the minimal saturated structure in this case is very small. This is 3R squared over 4. So as long as there exists a hypergraph where if we of size 3R squared over 4, well, adding any hyperedge will give us a pair of disjoint hyperedges. That is done by Ferretti in 1980. And then if we remove the restriction that this is we look at a set system instead of R uniform hypergraph. The extremal structure is 2 to the n minus 1, and that is easy to see that you still have a single vertex, and then you take all the set systems containing that element. And in that, for the saturation one, in that case, this is the same as the extremal number. It is quite easy to show why this is true. Basically, let's try to show its lower bound. Suppose we have a minimal saturated set system with less than 2 to the n minus 1 elements. Then, because it's less than 1/2, there exists some set A and A bar. Both are not inside. Okay, let's call this F. Both are not inside F because it's less than 2 to the n minus 1. Well, it's saturated, so why can't we add A into it? So we have A and A bar. But why can we not add A into the set? It must be the case that if we add A into the set, that we'll have a pair of disjoint set. So it must happen that there exists some B inside A bar, a complement such that A and B, and this B have to be in F. And then the same reason, why can't we add a bar into the set? It must be the case that there exists another C inside A, such that if we add A bar, we'll have a pair of disjoint set. And then this is also C is also in F. But then by the picture, you can see that B and C are disjoint, and they're both in F. So that contradicts that F is a saturated. F is a intersecting set system. So that's pretty easy. And then later on, there's also this. We can extend this to K matching free. Instead of having a pair of disjoint set, let's have K pairwise disjoint set. If we want to preserve this property, so the extremal, I think this is still open, and for many values of n and l is still not solved yet. So Kleitman showed that this is upper bounded by this quantity. It's basically what we can do is let's say we take all the sets, and then we start from the level n over k, all the sets with size n over k, and then we take all of the edges above, all of the sets above that level. That's something around this quantity. For the saturation set, there's a conjecture by Erdős and Kleitman in 1974 that this is upper bounded. Saturation number is upper bounded by 1 minus 1 to the 2 to the k minus 1 times to the n. Okay. In order to prove the upper bound, what we need is construction. So basically, the construction here is that we have we want to avoid k matching, k pairwise disjoint set. So maybe we can have k minus 1 elements reserved here, and then we take all the sets that intersect this k minus 1 element in arbitrary way. So so basically that number is this 1 minus 1 over 2 to the k minus 1 times 2 to the n. So Erdős and Kleitman conjecture that this is actually the lower bound also. However, it seems like this is a hard problem, a very challenging problem. So the best bound, I think, is by Butik, Letter, Sudakov, and Chen in 2018. They proved 1 minus 1 over k times 2 to the n. Okay, so any questions so far? Okay, so what we explore for this paper is different from the saturation in the above sense. They are more Ramsey flavored, okay, instead of extremal flavored. So what we investigated is kind of this common Ramsey flavored context where we have a color graph when we want to avoid monochromatic cliques. Chains and anti-chains in poset, analogous to Dilworth theorem, increasing, decreasing subsequence, the Erdős-Szekeres theorem, and then the k-caps in the point set, and also this Erdős-Szekeres convex point problems. They have analogous saturation problems in contrast to the extremal problems. Okay, so maybe I'll briefly talk about some of them, and then maybe some of the proofs maybe just talk about some of the shorter proofs if time allows. So let's first talk about saturation number in color graph. Okay, so what we do, so the saturation basically all the flavor is that we want to find some structure so that any structure extending that structure will break our property. Okay, so here let's assume G and G prime are all complete C-color graph. They may have different number of vertices. So what I do here is basically I'm restricting a large family, a family of graphs. And then, of course, this can be made more general by taking different, you can define arbitrary family of graphs. So here, both are taken from complete C-color graph. And then we say G prime extends G if G is a proper subgraph of G prime. That means basically that G prime can be obtained from G by iteratively adding a vertex and then add some colored edges from the new vertex to the existing G. So that's the definition of extension here. So naturally, how do we define saturation? Basically, let's say G is K1 to Kc, where C is the color. K1 to Kc saturated if G doesn't have any monochromatic kki of color I. But then any G prime extending G, okay, if no matter how you add a vertex and how you color the edges between the new vertex with the rest of the vertices, will contain a monochromatic kki for some color I. Okay, and then similarly, we can define semi-saturated by removing the restriction that G doesn't have monochromatic kki of color I. So this natural definition that as long as any G prime extending G contain a monochromatic kki, G is semi-saturated. Okay, so in that definition, what is Ramsey number? Ramsey number is basically the largest K1, K2 until Kc saturated graph plus 1, right? Depending how we define Ramsey number. And then, so naturally the analog is that was the smallest K1, Kc semi or saturated graph. Okay, that's the notation is SAT, and then depending on whether we talk about semi or not, adding an S in front. Okay, so what we can show now is that for two colors, the simplest case, two color for KL, right, clique of size K and clique of size L, the semi-saturation number equals to the saturation number is K minus 1 times L minus 1. Okay, and again, so maybe I think the proof is easy enough that we can just briefly go over. So for upper bound, we just need to give a construction of a color graph that is KL saturated, and this is basically very easy to see from this number. How do we do the construction, right? What we can do is, okay, we don't want any K clique. So let's have a K minus 1 clique, and they must have a K minus 1 clique. Otherwise, it wouldn't be saturation. It won't be saturated. And then basically, you can see from the number that all we need is to just K minus 1, L minus 1 copy of this K minus 1 blue cliques. And then what we can do is between this K minus 1, we just have all the red edges. And it's easy to verify that this is saturated, i.e., if I add any additional vertex, and then no matter how you color the edges, you can find a K clique, a K clique, a blue K clique or a red L clique. So it's easy to see because you have to, between this new vertex with the K minus 1 clique, you need to have some red edge. Otherwise, you have a K clique, blue K clique. And then if you do it for each of the one, because there are L minus 1 copies together with the new vertex, you have a red L clique. Okay. The lower bound, in order to the lower bound is not as easy too. What we can do is, usually this is, the proof is like if you add a new vertex, right? So because it's saturated, in the color graph, suppose we have, let's take a minimally saturated graph, KL saturated graph. Because it's saturated, I need to have some K minus 1 blue clique. inside it. Otherwise, I can create a new vertex and connect to every vertex with blue edges. And then if there's no k-1 click, there won't be a k-click. Then, well, we can give it some color. Let's say we color it with all the red color, right? And then for the rest of the graph, we also need to have k-1 click. So and then we do it. We color it with all the red. So etc. Suppose let's say we can find L-1 of them. Suppose there are L-1 of such blue clicks, then we are done, because that shows that saturated graph has to have k-1 times L-1 vertices. If it doesn't have L-1 such clicks, let's say L-2 such clicks, and then so basically all the other clicks are size smaller than k-1, and I can create this P, link all the P with blue colors. And then you can add this P into the graph. It doesn't create any blue K click red L click, because here the number of such blue clicks are L-2, so we wouldn't create L clicks too. So which violates the condition that this graph we are taking is saturated. So that's basically a very easy proof for this saturation number of KL. And for multiple colors, suppose C is greater than 2, there's a generalization for that. And basically the upper bound, what we can show is K1 minus 1 times all the way to KC minus 1. The lower bound is K1 minus 1 times K2 plus all the way to Kc minus 2C plus 3. Of course, you can switch the role of K1 with any other Ki. So if we observe this, and here the notation, what I mean here is because we always know that semi-saturation number is smaller or equals to saturation number. So I'm just using a short notation to see that both are bounded below and above by that. Okay, so if we observe it roughly, the lower bound, if we fix a C, the lower bound is roughly K squared. Suppose K1 or equals to Kc. K1 equals to K2 equals to Kc. Lower bound is roughly K squared. Upper bound is a polynomial of K, K to the C, around K to the C. So there are some recent developments after we published the paper. There's after we submitted to archive. The second bound we obtained for semi-saturation number of K color, and let's assume all the clicks are size K. It's upper bounded by. It can be also upper bound. Suppose we fix the size. Suppose we fix the click size K. And then you can see from here is a polynomial of the color. Suppose the color can grow forever. Is a polynomial of the color. So what Trent did is he basically he kind of figure out what's the asymptotic of the semi-saturation number. So for any fixed color, the semi-saturation number of KK is roughly quadratic. And then for every fixed click size, the semi-saturation number is also almost quadratic with respect to the number of colors, although there's a kind of a log factor there. So it's still open, can we narrow the gap between these two? And also, what he did is on semi-saturation number. How about for saturation number? Is it can we, instead of having K to the C, can we have a fixed constant that does not depend on the number of colors? So here, these are some of the open questions left there. Okay. Maybe it's a time to pause here. If there are any questions so far.
I have a quick question, actually.
Yeah.
Do we know, so in the case when there are only two colors, semi-saturated number is equal to saturated number. Do we know that they become not equal if the number of colors is more than two? Or they can become not equal?
Yeah, it seems, I think it's possible that when there are more colors, they start to be apart. Actually, we don't know that. That's why there's still this, we still don't know. So what Trent did, he know that the semi-saturation number is theta of k squared. But then we don't know yet whether the saturation number has an upper bound of n to a constant that does not depend on the number of colors. So we don't know.
I see.
Yeah. Okay. So let's talk about a different discrete object, poset. And I think by now it's already quite natural to define, what is the saturation for poset. In here, what we care about is the chain and anti-chain phenomena. So let's say there's two poset P and P prime defined on S and S prime respectively. So we say P prime extends P basically if we can restrict P prime on the set S, and then S will inherit the partial order in S prime. So for all x, y in S, x smaller than y if and only if x smaller than y in P prime. And with that, so naturally P is KL saturated if P contains no K chain, no L anti-chain, but then every poset, if we add any new element, any poset extending P will contain a K chain and L anti-chain, and naturally it's not completely contained in P. And then similarly semi-saturated if we don't need this part. Okay. So Dilworth theorem. So what is the largest KL saturated poset? That is exactly K minus 1 times L minus 1. It's the Dilworth theorem. And so the analog will be what's the smallest KL saturated poset. Can we construct some poset, saturated poset that is smaller than that? Okay. So in here we can actually get a pretty exact answer. For saturation number is exactly equals to the bound in Dilworth theorem. However, there's a difference between semi-saturation number and saturation number of poset here. In particular, it's much smaller for semi-saturation number. Is the minimum of 2k plus L minus 5 and k plus 3L minus 7. Okay. Maybe let me just briefly go over where does this two number coming from. Usually for this, so upper bound is always a construction. The lower bound usually are more technical. So with maybe let's just kind of see where does the two number coming from. So we'll just show the upper bound. Where does it coming from? Basically, we have two constructions here. First construction. Here I'm using k equals 6L minus 5, but it doesn't matter. What we do is we have an anti-chain of L minus 1, size L minus 1 here. And then we put two chains above. So here we can put k minus 1 chain, and then the minimal element is higher than all the elements in the anti-chain. And then similarly, we put another k minus 1 below all the elements in the anti-chain. And then it's easy to see that this is saturated, KL saturated, because if I add any element here, if it's incomparable with any of the elements in A, then we have a anti-chain of size L. Otherwise, it has to be, let's say, without loss of generality, higher than some elements in here. But then you can see that you can go down to form a chain of size K. This example is a little bit different. Here we have L-1 anti-chain, another L-1 anti-chain. I think this B is L-2 anti-chain. And then in here, we put K-3 size chain, a chain of size K-3 in here. And then all the elements in A is above the highest element of the C. All the elements in A1 is below the minimal element of C. Okay, and then it's a little bit harder to see why this is saturated, but basically, if we put a vertex in between, you can put a vertex here. P, it cannot be comparable. It cannot be incomparable to every element in A2, and then it cannot be incomparable with all the elements in A1. So it must be above some elements in A1 and then below some elements in A2. But then, basically, however, we have a new element in here. The reason why we didn't form a K chain here, it must happen that P is incomparable with some elements in the chain. Okay, otherwise we'll have a K chain. So the next step is that we look at this part. So how come they didn't form? Okay, so sorry, and B, every element B is incomparable to all the elements. Every element B in B is incomparable to all the elements, all the rest of the elements. The reason why we don't have an anti-chain here must be the case that P is comparable with some elements in B, and then by this relation, that B have to be comparable with some A in here, and which give us a contradiction. So it's slightly more complicated, but we can show it's F-saturated. And these two graphs basically give an upper bound for the semi-saturation number, and we can look at the structure of the saturated graph, and then you can show that this is also the minimal. It's also the lower bound, but it's more technical than the upper bound. Okay, is there? Maybe we can pause here. Are there any questions for the poset? So here it's kind of it's very nice that saturation agree with the extremal number, and also for sequences is also the saturation number also agree with the upper bound we have with the extremal number for the increasing and decreasing subsequences. Okay, so maybe let me kind of talk about for convex point sets, some kind of geometry. It's also easy to define the saturation number. Basically, what is here we can define both semi and saturation number. It's the size of the smallest point set in a plane, okay, such that adding any new point will either give us a new K cup. A cup is basically something like that. They are in convex position. Or a new cap, or a new L cap, something like that. Okay. And then semi-saturation is just remove the condition that the set itself already doesn't have a K cup or new L cup.
Cup be the L cap in the slides.
Oh yeah, sorry. New L cap. Yeah. So this still this kind of Ramsey flavor here. So what we proved is that okay, we still have this little gap, but it's essentially semi-saturation number for KL is between 2k plus 2l minus 10 and 2k plus 2l minus 12. Okay. I think maybe let's see how does, again, upper bound is much easier. Lower bound is usually more technical. So let's look at where does this 2k plus 2l minus 10. So in order to prove the upper bound, we need to give an example, a construction that is KL saturated. Means any new point will give us a K cup or L cap. So what we do is we start from a small example, and then we are going to extend it, okay, to this KL, to an example of this size. So let's start with a example with 10 vertex, and then we want to show that this is 5 saturated for the K cup and L cap. The reason why it is 5 saturated is it can be seen from the picture below. Okay, all we need to show is that any new point will give us a 5 cup, or a 5 cap. Okay, so we can just deduce the structure. Basically, we want to forbid, like no point can we add into it, so that we can avoid the 5 cup or 5 cap. So you can see there, you can basically look at each case. For each region, we can find four points, so that we can forbid this gray region. So if you add any point into the gray region, you're going to have a 5 cup. Similarly, if you add any point into this gray region, you are going to have a 5 cap. Okay, and then for each region we identify 4 points in this picture, and then when we union all of them together, it covers half of the region, and then by symmetry it also covers the rest of the half of the region. So that means no point can I add into the picture, into the plane, so that I can avoid a 5 cup or a 5 cap. And then from this example, what we can do is we can basically, with a little bit of extension, we can add k minus 5 point in here, k minus 5 point in here, and then the reason why it is saturated is very similar to the picture here. We can still forbid all the region in the plane, so that, and then we add up all the number of vertex together. This is 2k plus 2l minus 10. Okay, the lower bound is a little bit more technical. Basically, we have a lot of freedom to pick the point. So we kind of move the points along the way so that you can find a k minus 1 cap of find a k minus 1 cap, another k minus 1 cap. And then you can also find L minus 1 cup, I think. Oh, so here, let me change to L. Find another cup, another 2 cup of size k minus 1 here. And then the cup and cap doesn't overlap much. So then we get 2k plus 2l in there. Okay, but it's a little bit more technical. All right. So in the extremal setting, this K cup and L cap problem is used to show the corresponding extremal problem for convex n set, right? So here the second problem, a very natural extension is that, okay, if we have a point set that is in general position in the plane, we call it n-saturated. Okay, if P does not have a convex sub n set, a convex point sub point side of size n, but adding any extra point still in general position give us a convex n set. Okay, and then the corresponding extremal one is I think is an oldish problem, and that was the best bound is this breakthrough result by Andrew Sook in 2017, who proved that the maximum size of n-saturated point set is roughly 2 to the n plus little o of n. So here the analog is how about the size of the smallest n either semi or saturated either semi-saturated or saturated point set. Okay, and it turned out we don't know about the saturated analog of this problem. We don't even know what's the asymptotic. Is it linear? Is it polynomial of n? Is it exponential of n? We have no idea. So this is a wild open problem. For semi-saturated problems is a little bit easier. So let's say if we are restricted to R2, so all the points are in a plane. Okay, so semi-saturated problem of n equals to 2n minus 4. So just keep in mind that when we say semi-saturated, we allow the point set to have a convex n set. The only restriction is that adding any new vertex will give a new convex n set. So the upper bound is quite easy. So what we do is we want to construct 2n minus 4 points, so that adding any new points give us a convex n set. So what we do is we can construct a 2n minus 4, and then because it's it's even, so we can make the size parallel. For every edge we can identify an opposite edge, and then make them parallel with each other, with the opposite side. And it's easy to see that no matter whether you put the point P inside this point set or you put it outside the point set, this one is a little bit needs a little bit more work. You can always find convex, and you can always find a new convex n set here. And then for the last one, there's an extension of that result in RD. So this problem we can talk about it in d-dimensional space too. So here the setting is that we want to determine what's the semi-saturated number of a convex. Still want to find a convex n set, but then we allow the points is in a d-dimensional space. And then what we can show is lower bounded by this. Okay. So what's the proof? Lower bounded by n minus d plus n minus 2 over d. Okay. So lower bound here, in this case, we have a pretty clean lower bound proof. Suppose, let's say we have a semi-saturated point set with n minus 1 plus with this bound minus some positive integer minus s points. Okay, we want to show that it's not saturated. Okay, so that which means that I can find a point, add into there without creating any convex n minus 1 without creating any new convex n set. So the only thing we need to care about is all the convex n minus 1 set. Okay, as long as we adding a new vertex, adding a new point doesn't create a convex n set with all of this n minus 1 set, we are fine. So it suffices to show that if we look at the convex hull of all of this Fi, look at the interior of the convex hull, and then look at the intersection of all of them. If it's not empty, then we are good, because I can just add a point into the intersection of their interior of their convex hull. Because I added into the inside their interior, it wouldn't create any convex n set. Okay, and then by Halley's theorem, which is a theorem in discrete geometry, saying that in RD, if every d plus 1 set have non-empty intersection, then all of the sets will have a non-empty intersection. So basically, it suffices to show that every d plus 1 of this interior of the convex of Fi has non-empty intersection. Okay, that's by the number it will be pretty easy. That okay, if we look at the intersection of all of this Si, and we take d plus 1 of them, the complement of their intersection by Venn diagram, it has to be smaller than the sum of their. It has to be smaller than the size of the union of the complements, which is sum of the complements of each of the Si. But then because we only have n minus d plus n minus 2 over d minus s points, each of the Si have n minus 1 point because it's n minus 1 set. So the complements will have this many, n minus 2 over d minus s points. Okay, just by pigeonhole principle. And then because I have d plus 1 of them, so the intersection, the complements of the intersection of all of them have to be smaller or equals to this number. Therefore, the intersection of all of them have to be at least, if we use this to subtract this, it will be at least d plus 1. So the number is chosen so that this is strictly larger than d. And then now, because I have d plus 1 points, they are in general position. That d plus 1 points, which lie in the intersection of all of this convex n minus 1 set, they must form a non-degenerate simplex, which means that I can find a point in the interior of the intersection, which means that it's not saturated, since I can find a point to put in there without creating any convex n set. Okay, but then that's all we know. We don't know about the upper bound. Yeah, I think so. Apart from some cases where we know exactly we know the exact answer, a lot of the questions are still open, and it's not like they are hard. It's mostly because we haven't worked long enough on this. So if you are interested in any of the problems, feel free to work on them. You probably, with some idea, you can probably improve some of the bounds there. So I'll stop here. Thank you.
All right.
Thank you very much. Do people have questions? Are there any questions?
Yeah, can you give a couple of examples, like what are the problems that's still unsolved?
So we can just go above, and then each of the bounds there are some, each of the topics there are some unknown problems. So it seems like first of all, for this convex set, we don't know whether this is we don't know the asymptotics of this. So it's lower bounded by linear, but then is this the correct asymptotics? And then is there any upper bound? We still don't know. So for the and all of those we talked about is semi-saturation number. For this saturation number of convex endpoint, it's wide open. We don't even know the asymptotics of that. So even knowing what is the asymptotics would be very nice. And then for the k cup and k cap, there's a gap there. I think we don't know which one is the truth. Whether maybe we can analyze the lower bound a bit more carefully, maybe we can improve the lower bound, or there's a much better construction that can decrease the upper bound. We don't know. And then the poset one is fairly clear. For the graph case, I guess the most open one is for the. So what Chuan did, actually he submitted not long after we submitted our paper. The biggest problem left is he worked more on the semi-saturation number. So all of these are semi-saturated, and then we know is k squared, where k is the size of the clique. This 2 doesn't depend on color at all. So what for any fixed color is k squared. However, how about saturation number of C color of clique k? Is it upper bounded by this result is upper bounded by roughly k to the c? Is there a similar behavior as the semi-saturated number? Can it be k over some c prime, where c prime doesn't depend on the number of colors? That would be an interesting problem too. And then also, I think this, even for the semi-saturation number in general, semi-saturation number, I think it probably will be fine. It's mainly on the saturation number. can we improve the upper bound?
Okay, thanks.
Presumably, you can also look at other Ramsey-type questions and have a like a van der Waarden theorem or something like that, and have a saturation version of that.
Yeah. It seems like if we have an extremal kind of problem, then there's a saturation analog of that.
Mm-hmm.
But I think for graphs, the reason why saturation doesn't behave very nicely, I think, is not closed just for the extremal side, this saturation number. I think it's not closed under some graph property. So, and then also I think I'm not an expert on this, but I think the limit of the saturation number of NF over N does not exist. So it's kind of different it's a little bit different from the extremal setup.
Are there any more questions? If not, then let's thank Zhiyu. Can we unmute ourselves and clap?
Thank you.
And we will resume next week. Our speaker next week is Rose McCarthy from University of Waterloo.
Yeah, I just want to comment. Rose has a Georgia Tech connection. She was an undergraduate math major at Georgia Tech. Now went to Waterloo several years ago as a PhD student working with Jim Gillen.